Hey everyone, good afternoon. We have two quizzes due this Friday because one of them was extended due to the storm. So make sure you take both of those by the end of this week. And then also we won't have lecture next Monday. Okay, but we'll have lab. Just no lecture next Monday. I'll send an email out though to remind everyone. Okay? All right, so last week I got into microarchitecture and how to design the RISC processor, and I assigned lab 3. But there was we were pretty light last week, so I'll review what I talked about. I went over sequential logic, clocked logic, and in particular this register. And so you'll have in your CPU design, you'll need registers to hold values that are used in subsequent clock cycles. Okay, so you don't necessarily have to create a module for each register. All you need is this always underscore FF and then at pos edge clock, and then some output, and then less than equals some input, right? That'll give you the behavior of a register, of a flip-flop, I should say, a positive edge triggered flip-flop, register, multi-bit flip-flop. And then you can, depending on the case, you may want to also put reset logic in there and an enable. So the case for the enable is for, in our CPU, we need a way to get output out of the CPU and display on the hex displays on the board. So you're going to have a register in your CPU that's going to hold whatever value is being outputted on the 7-segment displays. Right now in lab 2, you just had a connection directly from the switches into the 7-segment displays. Now the displays themselves will be driven by your 7-segment decoder, decoders, but the input to the decoders will come from a 32-bit register inside your CPU, which will have to have an enable on it because you want to hold that value and only change it when you execute the CSRRW instruction that updates the output. You guys follow that? Does that make sense? Okay. Yes.
Doesn't the value come from the immediate field in that instruction?
No, the immediate field is, so the instruction is CSRRW, right? Is that right? Yeah, I think that's right. Yeah. And then you have a register, which is your RD, and then you have an immediate, which is 12 bits. This is 5 bits. And then you have an RS1. Okay. So if you're doing if you want to update the state of the hex displays, then you're going to put, for the immediate value, you're going to put F02. Is that right? F02. Right. This is in the lab sheet. Right. This is a magic number. Right. And this will be a don't care because you can't write, you can't read from the 7-segment displays and put them into a general purpose register, right? So you're going to use the RS register, like for example, will be 5, in which case you're going to take the contents of 5, contents of register 5 in the register file and send them to the hex displays by enabling this register that I'm talking about, this GPIO register, okay? So but on the other hand, if you want to read the inputs from the switches, use the same instruction, CSRRW. And in this case, the 12-bit immediate is going to be 0x0 F00, 0x F00. And then the RS is a don't care, and the destination is going to be what value you want to transfer the switch state into, what register, right? So in this case, this instruction will go out to the displays. We'll basically update the displays with whatever's in register 5, and this instruction will take the regs, in this case 5, will get what's coming into the switches. Okay? But the switches are only 18 bits, and that register here is 32 bits, so you're going to have to pad it with zeros, unfortunately. Some students take, we have those buttons on the board too. Some students just take the buttons and they kind of piggyback them here. You can concatenate the buttons in the upper bits of this if you want, if you have need for reading the buttons as well as the switches. The lab sheet only requires that you read the switches. You guys with me? But you have 14 extra bits that you can tag along, 14 extra bits. Okay. So this slide contains the, this is a RAM example, sorry. This slide contains the register file, but we give you this code in the Project 3 skeleton. Now, last week there was some confusion because I screwed up. Somebody asked me if there was a Lab 3 skeleton, and I said just use the Lab 2 skeleton, which is what you can do, except the problem is the Lab 2 skeleton doesn't have this thing in it, right? Of course, you could copy and paste it from the slide. But I think the version we have in the skeleton is a little different. This one was written by me. The other one was written by my student. They do this. They work the same way.
It has an error.
Does?
Yeah, it doesn't have the logic coming out. The one that's in the skeleton that I untarred has output and then the read data 1 and 2, but it doesn't have logic, so it failed. I put that in there.
Oh, interesting. It doesn't have the, oh, it's not declared as logic on output. Oh, interesting. Yeah. I wasn't aware of that. Okay. Yeah, so what she's saying is that these inputs and outputs have logic on them, right? Sometimes you don't need that logic. The time when you need, actually, you don't need it on any inputs. So the fact that I say input logic is kind of redundant. You can just say input, right? But output logic is needed whenever an output is driven by an always. What does that matter? I don't know. It's a weird holdover from Verilog. Okay? But notice that in this code, my output, read data 1 and read data 2, are not driven by an always. They're driven by a sign statement. So this is fine. I actually don't need the logic here, right? But in the version that's in the skeleton, it's written a little differently where the read data 1 and read data is driven by an always statement, in which case you do need that logic there. But I didn't know that error was in there. I'm surprised it didn't, I don't know how that didn't come up last semester or last fall. You guys with me? Okay. So that's the register file, and I talked about how this works. You know, if you read register 0, you always get 0. So this code allows you to write register 0 inside this always block, but if you try to read it, you'll just get a constant 0 back. And then this is the bypass path. So if you try to read and write the same register at the same time, you'll get the value being written. Okay. Then we have the ALU. This is also in the Project 3 skeleton. And I think this is the exact code that's in there. So it's longer, and there's 2 columns here. The bulk of the code here is this just one assign statement with these nested ternary statements in it, right? So depending on what the op is, you're going to assign a different value out of the ALU. Notice here that with the signed less than, we had to use this $ signed thing. So it changes the behavior of the less than. And same thing with the multiply over here. When we do the sign to multiply, we had to use the $ signed. You guys with me? Why is that? Because logic is assumed to be unsigned in the way that the Verilog operators interact with logic data types, right? But you can change that with this $ thing. So you don't have to understand how this works. You just have to be able to use it, right, and integrate it. But if you have any questions about that, let me know. Okay, so for lab 3, we have 22 RISC instructions. These are all arithmetic, comparison, logical shift, and 2 oddball instructions. We have this load upper immediate, which is needed to initialize the upper bits of a register, and this IO, the CSRRW, which I just talked about here. Most of the other instructions are behave in a similar way, except for the ALU opcode changing. Everyone with me? So basically, we can do number crunching, but we don't have any branch or jumps. So how can you write any useful program with this? It's kind of crippled, right? It's not Turing complete, right? Meaning that this CPU, after you implement these instructions, can't solve any, problem that's solvable by a computer. But we're going to take advantage of the fact that the program counter will increment from 0 to 4191, and then roll back to 0. So we'll get kind of a free loop in here. The code will loop on itself over and over again, right? So as long as we don't need as long as we just need one infinite loop and no decision instructions, then we should be good, right? So these instructions span 4 encoding formats, and I've showed them there. This is also listed, if you go to Dropbox, by the way, there's a come on. There is a RISC, if you go to RISC-V ISA-R version, this is a document that we wrote that has the encoding for each of these instructions. Okay? You can use that as a reference. I think they're also listed in the lab sheet too, right? Basically the same document. Okay. So these are different from MIPS, these encoding formats. They're a little strange. The thing that really confused me initially is we have this opcode and a function 3 and a function 7. So there's like 3 different function codes inside the R-type instruction. And you have to consider all 3 of them when you're decoding your instructions. Okay, so keep that in mind. I'll talk more about that in a few minutes. Okay, so this is a good starting point for your CPU if you don't mind inlining code. So this is the CPU module. This will go inside of your top module that's in the skeleton, along with your 7-segment decoders. And inside here, I have the instruction fetch logic as well as the instruction memory. So I've inlined this, which is maybe a little sloppy because you could probably envision this as outlined into its own like fetch module. But just to make it more readable, I just put everything in here. So you got the instruction RAM, the line of code that initializes it from the code that you export from RARs. So you just write your code in RARs and you just export it, and then it should, as long as the exported file name matches that file, and then you recompile resynthesize, it'll bring in your RARs code, right? You can't reprogram the software after you've synthesized. There is a way to do that, but we stopped doing it because no one used it, right? There is a way to actually sideload your code in, right, to the CPU. And then this just has the reset logic that resets the PC fetch to 0 and the instruction to a no op if you're resetting, and just increments the program counter and fetches the instruction otherwise, right? This assumes that the instruction just keeps marching forward, right? And because we don't have any branch and jumps instructions in here yet. Also notice that reset is active low. The reason for that is because we normally just connect it to one of the buttons, like key 0. And key 0 is active low, meaning when you push the button, it's 0, and when you release it, it's 1. Okay? Okay, so I already mentioned that. Okay, and then, so we're going to be creating a 3-stage CPU. We're going to allow the CPU to have one whole cycle to fetch an instruction because we're going to use a synchronous RAM for the instruction RAM. So it takes a cycle to fetch, and then the decode, execute, and memory. Of course, we're not really doing anything in memory stage because we don't have loads and store instruction. But the decode and the execute stage happen in one cycle, and then we're going to give it a whole cycle to write back. So 3-stage CPU, and then we're going to pipeline it, which means that we want to be able to support 3 instructions being executed simultaneously, except one's going to be in fetch, one's going to be in execute, one's going to be in write back. Does that make sense? Right? So we didn't do the 5-stage CPU just to make this a little simpler. Okay. Okay, so then I think I just started this on last week's. So I have a series of 3 slides or so that show the block diagram for the CPU. And for lab 3, all you really have to do is figure out how to translate this graphical schematic into Verilog. And a lot of the pieces we provide. So in this case, we have the instruction memory and the program counter. We don't give you a file for that, but it's in the slides, so you can copy that code from the slides. And then there's a register file which we give you, and then the control unit you have to write, and this is the most substantial part of this design is the control unit. So in the decode stage, once you fetch an instruction, the control unit is going to see, well, pretty much the whole instruction, but the relevant parts are the opcode, the function 3, the function 7, the CSR field, which is really just the immediate field, right? It's the upper 12 bits. So that's almost the whole instruction. Not quite. It sees most of the bits, but you could pass the whole instruction in, and if you don't actually treat all the bits as inputs, they won't be included in the logic. They'll get optimized out. Right? Okay, so the control unit has those as inputs, and then the control unit will convert those to outputs, which I'm not showing yet. There's no outputs shown here yet. So this just shows the inputs, and then the register file will get hard-coded bit fields from the instruction. For read data 1 and 2, that'll be the RS1 and the RS2, which are bit fields 19 down to 15 and 24 down to 20, which I can never remember. I always have to look that up. That's in the all the RISC-V instructions use the same bits for the source register and the destination register. So bits 11 down to 7 is the destination. However, there's a caveat for this one because the reading the registers is part of the middle cycle, the second cycle, but writing the result is part of the third cycle, the write back. So you have to stick a register here, and the register is just one line of code that just says always at pause edge clock, this gets that, whatever you name this and that, right? Make sense? Okay, and then the decoder, oh, right, I mentioned this too. It's sometimes, it may be helpful for you to create another module that renames these signals with special names instead of just referring to the bit fields in the instruction. Because I can never remember, like, the opcode is bit 6 down to 0. Sometimes I forget because MIPS is 5 down to 0, right? So you can create a decoder that just renames those signals where you'll have the instruction, you'll have a signal that will be just assigned with an assign statement from the instruction bits. Does that make sense? Right? Does that make, you guys follow that? So, like, for example, you would just say assign, and then you could say immediate underscore EX, and then just set it equal to the instruction underscore EX, and then the immediate bits, which is 31 down to 20, I think. Something like that, right? So this assign statement isn't doing anything logically, I mean, hardware-wise, but it's just kind of renaming it. And then when you declare that signal, you have to declare logic 11 down to 0, immediate underscore EX. So I've declared a 12-bit signal called immediate EX, and then I just have one assign that assigns it. So that way, when you're designing your CPU, it's easier to keep track of these parts of the instruction. Okay, and so the RARS has the ability to obviously assemble your RISC-V code and then dump it as just a list of 32-bit hex numbers in ASCII. So to do that, you just go to File, Dump Memory. Now these are not the default settings. You have to change the dump format to hexadecimal text. I forget what the default for that is, but you have to change that, right? But this will be your software assembler, right, for your CPU. So you don't have to worry about hand translating assembly to machine code like I did when I was in school. And I was writing code for the Intel 8085 processor. I had to do all this by hand.
What assembly were you doing? Is this the square root or like for the decimal?
Yeah, that won't be the square root yet because the square root requires the branch instructions.
So it's the decimal.
Because it has to make decisions about adding or subtracting. This will be, there's two programs. There's the binary to base 10 conversion and the test program. I'll talk more about those as soon. Okay, so this is the EX and write back stage. By the way, the naming is weird because we have 3 stages. What are we going to call them? I call them fetch, execute, and write back. But technically the execute is also decoding too. So the control unit is going to have to tell the ALU what to do. So the ALU has a 4-bit signal that tells it what function to perform. And in many cases, that's the only thing that really differentiates one instruction from another. Like if you have an add instruction or a subtract instruction, they're the same, except the ALU code is different, right? Does that make sense? So is there a clever way to translate func3 and func7 to the ALU op? Is there some pattern or something? I don't know. Probably. I haven't found it yet. Right? You just have to look up all the function codes and op codes and figure out what the ALU is supposed to be doing during those functions. Then we have reg-write. Now reg-write is one for each instruction that writes a register. Are there any instructions that don't write a register? Not really. I think the only one that does, if we go back here to the list of instructions. Okay, so all these instructions write a register. The only exception is the CSRW if you're setting the hex displays. If you're updating your hex displays, then there's no instruction, there's no register being written. Now you might say, wait, what about a no-op? Like what if you give it a 0 instruction? That shouldn't be writing a register then. Shouldn't be doing anything. Well, it turns out the no-op instruction, which is all 32 zeros, I don't remember now. What is it? It maps to like a shift instruction, I think. If you look at the bits, so like, in other words, if you look at the opcode, the function 3 and function 7, if they're all zeros, what instruction is that? I believe it's a shift, right? However, which writes a register, right? But the destination register is also 0. And remember, if you write to register 0, it doesn't actually write to register 0. So a no-op actually will write to a register, right? So the only exception is the CSRW if you have if the immediate is, if it's a CSRW and the immediate is FO2. Okay? So that signal seems kind of redundant, right? But there'll be more instructions that don't write register in the next lab, so we still need that reg-write. So the reg-write will pretty much almost always be 1. But we still have to delay it by 1 cycle. So we have a reg-write EX. So that's basically whether the instruction in the EX intends to write. And then reg-write write back is if that instruction is actually writing when it gets to the next cycle, 1 cycle in the future. Okay? So that register will provide that delay. And then we have reg-select, which is, this is where this is probably the most complicated part of the control, the data path control, because this mux is controlling, well, it's not really clear what it's controlling because this port isn't labeled. But the output of this goes back to the reg file. And the intention here is to decide what to write, what value to write, not where to write, because the where to write it comes straight from the instruction, the RD field, right? This mux is controlling what value I'm writing to the register file. And in this lab, there's 3 options for that. There's the GPIO in, which would be when I use this instruction. So if I do a CSRRW with F00, I want to read the switches. And so in which case that reg select needs to be set to 0. Or it could be the upper bits of the immediate 20, sorry. There's 2 immediate fields, right? There's a 12-bit immediate field and there's a 20-bit immediate field, depending on what instruction you're looking at, right? This is the 20-bit immediate field. This is the upper 20 bits of the instruction, and it's only used for the LUI instruction, load upper immediate. And then the third option is just whatever the ALU is spitting out, or what it did spit out in the previous cycle. Okay, why do I say that? Because the select for the write enable is also being delayed, right? So this mux is a combinational logic circuit, but it's actually doing the work in the write back stage, meaning that all of its inputs are reflective of whatever instruction was being executed in the previous cycle, right? So you have to delay everything going into this mux. This is the most common mistake that students make in this lab, is not delaying one of the signals in, the write back stage. Make sense? Now you can, by the way, you can name these signals whatever you want. Notice that I named this AEX, right? So there's an output from the reg file called read data 1. The port is called read data 1, but then I rename it as AEX, right? Why A? Because A is the port on the ALU is called A, right? Okay, so this signal I named write data, write back, and then reg write, write back, which is just the signal that tells the register file to write. It's connected to the enable, the write enable. Right, you guys remember that from the reg file? Yes?
You kind of simplified the reg file to the ALU on this particular graph. Is there actually the mux that right there?
This one? Yeah, I haven't gotten to that. Yeah. No, I haven't gotten to that one yet. So that's a second mux. This one controls what goes into the second input, the B input on the ALU. And the choice that, what's the choices you have for that? The choices for that are whatever comes out of the register file, right? Or something else I may want to add, put in the second input, which would be the immediate value, right? But it's a 12-bit. Now the immediate, I'm not showing it, I think I show it in the next slide. The immediate value is, yeah, here it is. The immediate value, which is instruction 31 down to 20. This is the 12-bit immediate, right, from the I-type instruction. You have to sign extend that to convert it to 32 bits. And then it goes into that mux. So this mux is controlled according to if you're doing an R-type or an I-type instruction, essentially, right? If there's an immediate in the instruction, then you should set that mux to 1, otherwise it should be 0. This is one thing that RISC changed in MIPS. MIPS used to say, if you're doing an AND-I instruction, you should 0 extend. And if you're doing an add-I instruction, you should sign extend. So we used to have 3 inputs on that mux. We had to have the register, the sign extended, and the 0 extended immediate, right? Because their reasoning was, well, there is no sign bit if you're doing logical instructions like an AND or an OR or an XOR. Sign bit is meaningless, right? But then RISC came along, RISC-V just said, yeah, just sign extend, even logical instructions. mean, because it, simplifies the hardware, obviously, is the reason for that. Okay, so this is the whole CPU. I put everything together here, but this doesn't include the decoder. This is without the decoder. Yeah, no decoder. So this is everything I've shown. The only exception is that you'll notice that for the control unit is using the fields, the instruction fields, as opposed to the renamed signals. It's up to you if you want to do that or not. So pretty simple, right? So this translates into, I don't know, 30, 40 lines of code, and you have a working RISC-V CPU. That's pretty incredible. Of course, when you translate it to gates, it's tens of 10,000 gates, maybe, something like that. I have to check that. I'd guess about 10,000 gates. So 40 lines of Verilog, very simple, but you could never do this in 211. You couldn't build this in 211 on breadboards. It would be way too complex for that, but not really too much code in terms of the system Verilog. Okay, so how do you build the control unit? As I mentioned, this part is actually this part is going to increase your code size, but it's just basically an if then else, right? So if, for example, the instruction that's been fetched, which is whatever's on instruction EX, if that's an add, well, how do I know it's an add? Well, you have to look at funct7. You could ignore the immediate because add doesn't even have an immediate. So that's a don't care. I put an X there. And then funct3 is 0. And then the opcode is 33. So you asked if the R-type instructions have a 0 opcode like they do in MIPS. They don't. I think they have. They may all have a 33 opcode though. But don't quote me on that. I don't remember.
They do the ones that we're doing all that.
Okay. So maybe that's the pattern. Opcode 33 means R-type instruction. So the way I handle this though is I just let the synthesizer figure out what all these bit patterns are. I just use an if then else, right? So, I just basically build the truth table with if then else. Okay, so if it's an add, I have to set, so those are my inputs, right? My input is funct7, funct3, and opcode, and I have to set ALU op, ALU source, reg select, reg write, and GPIO write enable. What's GPIO write enable? That's when you want to update the hex displays. That's only going to be set when you do this guy, CSSRW, right? So ALU op should be add. What's the add ALU op? Well, now you have to reference this table. How do I add? It's 0011. So I got to put 3 on the ALU op. And then subtract is 0100, multiply is 0101, and set less than is 1100. And those come from this table. So unfortunately, you guys are going to have to just refer to this table because no one's going to memorize that, right? ALU source is 0 for all of them because they're all R types. Reg select is 10 for all of them because they're all writing the data that comes out of the ALU, right? Reg write is 1 for all of them because they all write a register, and GPIO is 0 for all of them because none of them update the hex displays, only this instruction does, right? Okay, how about AND, ANDI, SLL, and SLLI? Well, the opcodes, again, you just look up in the table. SLL and SLLI, even though they're different instructions, both do a shift left logical, so the ALU op is 1000, right? ALU source is going to be different now because now I have to differentiate. I've got a mixture of R-type and I-type. So this guy's an R-type. How do I know it's an R-type? Well, you can look it up, but also there's no I after the mnemonic. Most I-types have an I at the end of the mnemonic, and there's no I. So, but then you might say, well, how do I know it's not like a U-type or? But it's R-type. This guy's got the I in it, so it's going to have an ALU source of 1, and then R-type and I-type here. By the way, this is swapped in This is different in RISC-V than MIPS. In MIPS, this would be, SLL would be an R type. Oh, which this is too, yeah. And SLLI is a I type. But there's no I type shifts in MIPS. I guess that's what I meant to say, right? I type shift instructions don't exist in MIPS. Okay, reg select is, I think, pretty much always the same as 1, 0. Yep. Reg write's always 1. GPIO is always 0, right? Okay, now we've got LUI. And the CSRW is split into 2 rows of the control table. This is not typical. This is not how RISC meant this to work. But this is the special case for us. So we're going to treat these 2 separately. In real RISC-V instructions, the CSSRW always writes the register file because it does an atomic swap. In our CPU, it doesn't. So we're going to have to look at the immediate 12 as an input to the control unit to differentiate these 2 variants of the CSRW. So ALU-op is actually a don't care. Now, make sure in your control unit you drive the ALU-op even if you have these instructions come in, because you don't want to create a latch. You don't want if you don't set that, then the system Verilog is going to assume that it doesn't change, and so it's going to infer a memory there, right? And then when you go to, probably what will end up happening is when you go to synthesize this, it's going to go from a minute to 5 or 10 minutes, right? Because the latches make it harder for the synthesizer to achieve timing closure. So now you can, what do you do? What do you set it to? You can set it to 0, or you can actually set it to X. If you set it to X, in Verilog, X is a don't care. If it's in the context of an output, which is wildly confusing. In VHDL, it's hyphen, and it makes more sense in VHDL. VHDL has a hyphen for that. And you might say, what's the problem with X? Because X is used for conflict and don't knows, and it's used for other things, right? But it's also don't care. ALU sources also don't care. Reg select is. Now, reg select is different. In fact, this one, reg select is a don't care if I'm reading the writing the hexes, but if I'm reading the switches, I have to set this to 0. This guy. And if I'm doing the LUI, then I want it to be this guy, 1. Okay? So the control unit should be combinational. There's no there shouldn't be any memory in the control unit, just to clarify that, right? You just, it's an if then else, but there should be, everything should happen in one cycle, asynchronously with the control unit. In other words, there's no clocking, there's no clock in there. Reg write is always 1, except for the, as I mentioned, the hex display should be 0, and GPIO write should only be 1 when you update the hex display. Is this clear, by the way, that what that GPIO write is? So GPIO write is this guy up there. It's an enable for that register, right? I always get, I usually get a lot of questions about that signal when everyone gets going on this. All right, so here is the control unit table, but it's not complete, because if it were complete, then we would give you pretty much the whole lab. So not all the instructions are here. You'll have to fill in the rest. Okay, but you can refer to that slide. Okay, so how do you test the CPU? Well, that's a good question, because I still haven't figured that out. I've not figured out how to test the CPU. The way that we do it is really hackneyed. So basically, you take this test program and you initialize your instruction memory with it. But then, in order to know if it's working, you can't write a self-checking test bench. The only way to know if this is working is to, in the simulation environment, in ModelSim, you have to open your register file, the contents of your register file, which is something you can plot. And then make sure that as it runs, each one of these values that I have noted in the comments are written to that register. we've been trying to figure out for 20 years how to do this in a way where it can be a self-checking test bench. The reason why it can't be a self-checking test bench is that a self-checking test bench would have to be able to see something coming out of the CPU to indicate if it's working. Right? Now you might say, what about the hex displays? Why not just have it write the hex displays at the end? And if it writes that, the test bench will see the hex displays being updated. Yes, that's correct, but that's only the last. In order for that to happen, every single instruction would have to execute perfectly. What we really want is be able to test each individual instruction in a self-checking test bench, and there's no way to do that. Unless the only thing we thought of is you could do this thing where you expose the register file write data and write address ports to the outside world, like make them ports. Then you could use that. Right, that's one option, but no one ever wants to do that because then you have to write test vectors that have these values in them, right? But you guys still have to write a test bench, so you can just key it off of the hex display value at the end. It's just not a great test bench because if it doesn't work, you still have to go in and try to figure out what instruction failed, right? Makes sense? These instructions build on one another. Not all of them, some of them, right? So you initialize register 1 and 2, and then you set up register 3 as a function of register 1 and 2, and also, in this case, 3. So there's a dependency chain that goes through this whole set of instructions. So I think most of them, yeah. Well, this XOR is an exception because this XOR just relies on register 1 and 2. But most of the instructions depend on previous instructions. So if one of them goes bad, everything after that dies. Yes?
We have to use that exact program?
Yes.
Okay, because I wrote one that basically does the exact same.
Yeah.
Okay, so.
We want you to run this one just as a common test case. You can obviously write your own. This is not a great test program. I mean, the only thing it does is test every instruction at least once. You should test corner cases. So what's a corner case? Well, what happens, for example, if you have a CSSRW instruction and you don't have F00, F02 in there, right? What happens then? Well, this test bench wouldn't even exercise that possibility, right? So, right, what happens if you have a positive value for the immediate instead of a negative value, right? So there's corner cases that we don't. There's a lot of corner cases that we don't test, but this is just an example. Yes.
So this doesn't have any dependencies that would require stalls in the pipeline?
No, stalls are just for, we're going to need those for the branches.
But this won't need that.
No. Yeah, we don't have the ability to stall. One thing I've wanted to do is to add a multi-cycle divide instruction in here where if you have a divide instruction, it would stall in order to give the divide time to work. But we haven't done that yet. But that would be an example, like if you have a multi-cycle instruction, you would need to stall for that. Okay, so that's program 1. Program 2 is binary to decimal conversion. So we want to be able to have the CPU perform a variation on lab 2 where instead of doing a hex conversion from the switches, we want to do a decimal conversion. So if you put in like 1111, it should show 15 instead of F, right? So if this program works, you won't see anything from A to F on your display because it's going to give you a decimal output, right? So how do you do that? Well, it's pretty much just a divide and modulo thing where if you take a value and you take a modulo by 10, it'll give you the least significant base 10 digit, right? And then if you divide it by 10, it will delete the least significant base 10 digit. So you just do a modulo to extract the digit, followed by a divide to delete the digit, and then you repeat that process, right? The only thing tricky about this, though, keep in mind that this program is generating digits from right to left, not from left to right. So ultimately, when you want to display your value to the hex displays, you have to have all the digits in one register, and they have to be in the correct order, which means when you run this algorithm, you got to make sure you put the digits in from right to left. Okay? Now, the obvious question is, well, we don't have divide or modulo, so how do we get around that? Okay, so for this, we're going to use a fixed point again, like we did before. So instead of dividing, we're going to just multiply by 0.1. So the 0.1 is going to be 0.1 with all fractional bits. If you don't do it that way, you're going to have too much round off there, and the program's going to screw up. Actually, even with 32 bits, there may be cases where this program screws up. But I haven't nailed down exactly what those are yet. Right? So in other words, if you take a 32-bit integer, right, and you do 2 to the 32nd power, which is 4.2 billion, right, and you divide that by 10 and put the value in the register, that will represent 0.1 because it's 0.1 through the whole range of a 32-bit number. You guys with me? Right? So it's roughly 429 million. That's your magic number. That's your magic number that means 0.1. Okay? If you multiply that by an integer with 0 fractional bits, then you get a 64-bit result, but you only care about the upper 32 bits of that product, which are the integral bits, right? So this is simpler. Remember, this is simpler than the program you guys already wrote in Lab 1 because you don't have to worry about taking bits and recombining and shifting across 2 registers. All you have to do is do a multiply HU. Do a multiply HU between a number and 2 to the 32nd divided by 10, right? And that will give you the divide by 10. You guys with me? Right? Very simple. No, you don't have to bit twiddle with this one. However, what about the modulo? Well, after you do the multiply, if you look in the lower bits of the product, you're going to get the fractional part. So if you multiply, like, say, 5 by 0.1, you're going to get 0.5, right? So that 0.5 will be the modulo. That's going to be in the fractional parts of the product, right? But how do you recover it? Because that 0.5 will be expressed as basically halfway. It'll be 2.1 billion. It'll be halfway through the range of the 32-bit number, right? But how do you get the 5? Well, then all you have to do is take the fractional part and multiply that by 10, right? And then you look in the upper bits of that product and you'll have your 5, right? So what I'm saying is that you have to do 3 total multiply instructions. You need 2 multiply instructions in order to multiply your value by 0.1. Why do you need 2? Because one gets the upper bits of the product, which is the divide, the quotient, and the other one is going to help you recover the modulo, which is the fractional part, right? Then you need a third mul HU to multiply the fractional part by 10 to recover the modulo value. Right? So there's 3 multiply instructions, you can do the divide and the modulo steps together. Okay? But note, it's just a matter of grabbing those values and making sure you don't overwrite values you need to retain. Now you might say, wait a second, I got to do this 8 times though, 1 for each digit. Well, you don't really need to do it 8 times because if you put all the switches up, there's 18 switches. So if you put all the switches up as your input, that's going to be 2 to the 18th power minus 1, which is 262,143, which is only 6 digits, actually, not 8 digits, right? But do all 8 digits because in Lab 4, we're going to need all 8 digits, okay? But then you might say, what about, I don't have a loop. How do I do a loop? How do I loop through 8 digits? You can't. You're going to have to unroll your loop, meaning copy and paste 8 times, the loop body 8 times, okay?